So R is A minus DQ. It's the smallest value. And so it's clear that this is unique. So it's the smallest value, the smallest element of our set. So that's definitely going to be unique. But what about Q? So what would it mean? So what if Q is not unique? So what we're going to do, it really, I shouldn't put this in the proof. This is really just thoughts I'm rambling on. But let's suppose, so to show Q is unique, let's suppose that it wasn't, or let's suppose that there's two different values, A minus DQ and A minus DQ prime. Okay, so let's call it Q and Q prime. So let's suppose that R is achieved by two values. If you know that R is unique, then we can just use that to get uniqueness of Q as well. There's really not too much to show. This implies that A minus DQ is equal to A minus DQ prime, and then subtract A, divide by negative D. And from there, it's a short step that Q is equal to Q prime, okay, giving uniqueness. So that's one proof. Okay, so that's the proof using the well-ordering axiom. The second proof, and again, one is enough, but I think the second proof is important enough that that I want to talk about it, spend at least a little bit of time talking about it. So the second proof, we want to prove that there's unique integers Q and R such that A is equal to DQ plus R, where R is in between 0 and D minus 1. Okay, and here's the second proof. This is, I don't know, it's tricky is the wrong word, but you can just explicitly say what Q and R equal. So for example, you can take Q to be the floor of A over D, which of course it is. So if you have Q being A over D, then R is going to be A minus DQ. And of course, this is unique because whatever A and D are, that's a, you could think of this as a function from, so you could think of this as the output of a function from all the possible A's and D's, right? So you can get some value here, but whatever your A and D is, there's only one output that you would get there. And once you have that, then you can compute R by plugging in for Q that way. What we need to show is the second part, okay? And we need a few facts about the floor function. So this again is an aside, and I'll leave these facts to you to prove. But fact one is that the floor of X is less than or equal to X. There's, that's almost part of the floor function's definition, right? It's the floor function is the largest integer such that it has this property that is less than or equal to X. So the floor of pi is 3 because that's the largest integer less than or equal to pi. So fine, nothing really there. Fact two is a little bit more, and that's that not only is the floor of X less than or equal to X, but X is strictly less than the floor of X plus 1. Okay, and so X has to be strictly less than the floor of X plus 1. And if you like, you can even combine these into basically a string of inequalities here. So you get that the floor of X is less than or equal to X, which is strictly less than the floor of X plus 1. Okay, you can't have X being equal to the floor of X plus 1 because that would imply, first of all, that that X is an integer, in which case the floor of X is just X itself. So that's impossible. So I'll let you think about how you would write that up in detail, but these are the two facts that we need. So let's move that to the end, but just something to keep in mind. And this gives us what we need about R. So the first thing is that we need R to be greater than or equal to 0, but that follows since A minus D times the floor of A over D is greater than or equal to 0, as the floor of A over D is less than or equal to A over D. So just move this D term down, right? Divide both sides by D and we're done. Remember, D is a positive integer, so the inequality stays in the same direction. So I will leave that to you to finish that out. Finally, we know that R, so A minus D times A over D, is less than or equal to D is the same as saying less than D, because these are integers. So when we're talking about integers being less than or equal to D minus 1, that's the same as saying strictly less than D, right? So if you have, you know that something is, you have some integer that's less than or equal to 7, well, that's the same as saying you have an integer that's less than 8, right? I'm not saying anything interesting or new here. But this follows because, so this is less than D by the following reasoning. So let's again divide both sides by D. So this follows since, let's just build it up the way I want to do it. I'm going to use this fact, the second fact, that A over D is less than the floor of A over D plus 1. So that implies that A over D, how do I want to do this? A over D minus 1 is less than the floor of A over D. And therefore, if I multiply both sides by D, again, remembering that D is positive, so it respects the inequality, we get that A is less than D times the floor of A over D. Okay, so A, excuse me. Yeah, I have everything I need to. I just need to organize it a little better. So if I multiply both sides by D, what happens? We get A minus, I'm trying to do too much here. A minus D is less than D times the floor of A over D. Oh, I see. And therefore, let's move this term over, and let's move the D over. And that tells us that A minus D times the floor of A over D is less than D. That's perfect. Okay, that's exactly what we wanted because this left side is R. So R has to be strictly less than D, and that's exactly enough. So both of these ideas, I think, are important enough that they kind of deserve their own proof, but here's two different proofs, okay, of a fact that we kind of take for granted.